You made it. The last conceptual overview video of Lecture 6. So the past couple of videos, the past 40 minutes or so, y'all have been wading through all of these new mathematical little widgets we're going to use, all these individual things like angular momentum, angular velocity, definitions of theta, definitions of moment of inertia. Now is when we finally tie them together into something physical and meaningful. So this is like the paramount lecture. No equation that we write here is not important. So all of the equations that are in these following slides are like top tier. Make sure that you can read and understand what each of them means. Okay, let's hop into it. Cool. This last video is going to be on torque and angular impulse, ang-j, angular impulse. So this is when we really get to talk again about changing angular momenta, changing angular velocity. So what are a torque and angular impulse? So torque is analogous to force. Torques cause changes in angular momentum. Torques cause, as a result, changes in angular velocity. Yeah, so torques are kind of like forces, except for angular. They change the magnitude and sometimes direction of angular velocity. Angular impulse just describes that change. So an angular impulse is just a change in angular momentum. Change in angular momentum. Okay, now let's get a little bit more explicit, a little bit more precise. So torque, it describes the rate of change of angular momentum. In particular, let's just write this down. This will be on the next slide too. But in particular, the change in angular momentum is torque times time. Okay, times delta t, I guess I'll say, times the change in time. Okay, so torque comes from forces. So here's the classic formula we use to describe a torque due to a single force. So a torque is r, displacement vector r, times f times sine of theta with respect to those two, rf. Okay, so this equation by itself, totally unintelligible. What is r measured relative to? What is it measured to? What's f? Like what happens with f? Where is this coming from? So let's get concrete. This situation describes very well the torque experienced by a rigid object experiencing a force some distance away from its pivot point. So say I've got an object. I'm going to again make it a seesaw, but that's just because I like seesaws. So I'm going to make it a seesaw. Boom. And the thing I'm interested in is the torque on the board, the torque on the part of the seesaw that is free to move. Here's my seesaw. Boom, boom. All right. My pivot point, let's go ahead and mark it, PP. Okay. And again, I've got a force that's acting on this board. Let's say, just for my convenience, let's just define some angles here. Let's zoom in, make life a little easier. So let's say that the angle that this side makes with the horizontal is, I don't know, eyeballing it, let's call it 15 degrees. And let's say that I've got a force some distance away directed straight down. Maybe it's a gravitational force. Maybe I've put a mass on there. It doesn't really matter where this force comes from. It's just a force that I've applied at this point in space. There's my force. Okay, so the torque caused by this force isn't just the force itself. It's the force scaled by the perpendicular distance. So I say that, let's get a little bit more concrete yet again. Here's my r, the displacement vector, relative to the pivot point. So r is a distance, basically, a distance along the object that's rotating, a distance along the object toward the point where the force is being applied. All right, now we've described r, sick. We've described f, sick. We're looking for torque. the last thing I want to do, and really what I should say, sorry, this is a bit of a typo here. Magnitude torque. Magnitude torque. Let me fix that on my slides as well. Okay, the last thing to describe is this theta, this angle. So this theta is distinct from the theta we use to describe like the orientation of the rod. It's a totally different theta. This theta refers to the angle between the force vector and the r vector, the force vector and the displacement vector. So what I mean when I say the angle between them is if I were to draw each of these from the same point, there's r, here's f. If I were to draw each vector from the same point, as if they shared an origin, f, the angle between them is theta rf. Theta rf. Now, alternatively, because of a certain symmetry of sine, you can also just measure this angle. So these two angles in general are going to be symmetric about 90 degrees. So like here, this angle would be 105 degrees. And this angle would be, let's see, 180 minus 15 minus 90 makes 75 degrees. 75 degrees. And if you put both of those numbers into the sine function, 105 and 75, you get out the same answer. So these are two ways you can measure the angle. One is to just take both vectors, put them on the same origin, and then measure the angle. Or if you have it in this form, you can just find this angle. The angle kind of like from the head of R to the tail of F. Okay, now intuitively, what this formula tells me is that torque increases the farther away I apply my force, the farther away R is, the greater the force, and the more perpendicular my force is to my displacement vector. Okay, so imagine this for a second. Say that I had, again, a CD, my archetypal example. If I apply a force directly in toward the center of the CD, I'm not going to make the CD rotate, right? If I do it directly in, it's not going to rotate. If I put a little angle in it, it'll rotate, right? So if I rotate it like this, then it'll rotate. If I put a force directly away from the center, same deal. It's not going to rotate. The only way I can get it to rotate is by putting a force in some direction that at least has a part that is perpendicular to the displacement from the pivot point. So there's my force in blue. Here's my force. Now my pivot point is right here in the middle, which means that my r vector, my displacement vector, would be something like that. This is an example of a force that would cause a rotation. Here's an example, and I shouldn't say a rotation, an acceleration in rotation, so changing the rate of rotation. Here's an example of a force that wouldn't, right? In this case, theta is 0 or 180, symmetric about 90. Either way, sine of 180 is equal to sine of 0, which is 0. So there is no torque in this situation. Torque is maximized in this situation when my force points at an angle of 90 degrees to the displacement from the pivot point. So if I put my finger right here and push directly in this direction, as indicated by force, that's what would cause the most change in angular velocity for the amount of force that I can provide compared to any other angle. Okay, so the units of torque, units, is a Newton times a meter. It's a force times a distance, which has units of kilogram meters squared per second squared. So those are my SI units for torque. It's a Newton times a meter, a force times a distance. The sign doesn't have units, right? Okay, now, in your DLs, you'll see that there are two ways to think about this equation. One using F perpendicular, where F perpendicular is magnitude F times sine theta RF, and one using R perpendicular. So in either case, it boils down to this equation. It's just a question of which is easier to think about in your problem. So most of the time, it's going to make sense to think about F perpendicular. the component of force that points directly perpendicular. There we go. There's F perpendicular. There's F parallel. So here's parallel. Here's perpendicular. The perpendicular component, the component that's perpendicular to R, that is placement vector, is the only part that actually matters. The parallel component doesn't contribute to the torque. Cool. And that's just F times sine theta. Similarly, you'll find that sometimes it's more intuitive to use R perpendicular. But regardless, which is, so R perpendicular, there we go. It's just magnitude R sine of theta, RF. But again, I would say this equation is like low on the list of equations to know. The most important thing is to develop some intuition for when it's better to use R perpendicular and when it's better to use F perpendicular. And you'll hopefully develop that some in DLs and in problem sessions. Okay, the very last thing I wanted to mention is this notion of additivity. So if I've got that same seesaw, let's go seesaw, and I've got multiple different forces acting on it now. Say I've got a kid on one side and a kid on the other side. Happy kid and sad kid, or angry kid. Let's make this is angry kid. Everybody's been there. Or maybe not. I've been there. All right, angry kid. So we got angry kid and happy kid. They're each doing a force, right? They're putting a force on this seesaw around this pivot point. R1, R2. Each one is putting a force on the pivot, or on the seesaw. Here's force 2. So each of these induces a torque. This one makes torque T1. This one makes torque T2. And those two torques are additive. So, yeah, so I say the total torque is just torque 1 plus torque 2. Whichever torque is bigger, so to speak, is going to be the one that causes the rotation. So if the torque caused by person 1 is greater than the torque caused by person 2, the rod will begin to rotate this way. Okay, torques also follow the right-hand rule. So the torque due to this first kid, the blue kid, is going to be pointing into the page. Sorry, that's not the symbol for into the page. Here's into the page. So torque 1 points into the page. It tries to make the rod rotate in the clockwise direction, so into the page. The second person, is inducing a torque that tries to make the rod rotate counterclockwise, out of the page. And again, just line your hand up. So I line my fingers up with the direction of the force, basically. And I keep my palm oriented inward toward the pivot point. And I get a torque that points out of the page toward me. So when these two vectors add, there's one vector that points into the page, one vector that points out of the page. The sum of them is going to produce a vector that points either into the page or out of the page. And that tells me the direction of the overall torque, the total torque. All right, second to last slide, angular impulse. So angular impulse, ang J equals delta L equals tau delta T. So this is like the one that I use to describe the what's actually going on, quote, quote, what's actually going on. How changes in angular momentum are a result of torques and time evolution. So as time goes on, a torque causes a change in angular momentum. This is the formula that I would hang on to. So angular impulse just means change in angular momentum, and it's caused by a torque times a change in time. So if I have a record player, and I'm just starting it up, initially its angular momentum is 0. Here we go. So initially, it's just 0. Over time, and I'll write it in terms of magnitude and direction. How's that? Over time, as I induce a torque, let's say that I've got the central point now is causing a torque that is trying to get us to spin this way. In other words, a torque that points into the page. Cool. So I've got a torque that points into the page. Over time, the angular momentum is going to increase. So after, let's say, 2 seconds, L final after a delta t of 2 seconds, there's going to be an angular momentum of whatever that torque is times 2 seconds. And the angular momentum is going to point in the direction associated with this rotation. So angular momentum final is going to point into the page. So say that the torque is, I don't know, 15 Newton meters. So a torque of 15 Newton meters times 2 seconds would result in an angular momentum of 30 kilogram meters squared per second. So this formula is very general. It's true for individual members of a system. So if I've got one part of a system that is being, say, collided with by another part of the system, that's going to induce a change in the angular momentum of the subsystem. So say I've got an asteroid, it gets hit by another asteroid as a glancing blow. This first asteroid is going to start rotating, right? And that's rotation was caused by a torque from the first asteroid. So it's true for individual members of a system. It's also true for a whole system. So if I define a pivot point somewhere and I measure out, here we go, these R's, R1, R2, etc. I can find that the angular momentum is either conserved in the case of zero external torque or changes according to the magnitude of that external torque. So for a closed system with no external torques, we have no change in the total angular momentum of the system. Which brings me to conservation of angular momentum. This is our big law. This is the law which governs how rotation translates between members of a system. Okay, so stated as an English sentence, the law of conservation of angular momentum tells me that the change in angular momentum for a system with no net external torques, is 0. Boom. So angular momentum doesn't change as a function of time if there are no net external torques. If there's no external forces, say, that are causing torques. So what that tells me is that if the universe is like everything that happened since the Big Bang, if the universe is not affected by some distant universes very far away or something silly like this, the angular momentum of the entire universe is conserved because there's no net external forces on the universe, presumably. No net external torques on the universe. Cool. Any rotation we experience is just somebody else's rotation recycled.